So Barry will talk about GreenFunctions, Hadamard expansions, and Riemann Tensor Canonicalization.
So I've got a few slides to kind of explain the mathematics and the physics of the problem that I've been working on for several years, and then after I've kind of explained that, I'll get to actually a demonstration in Mathematica using xAct. So this is work that I started, I guess, near the start of when xAct was around, about 15, nearly, not quite 20 years ago, maybe 15 years ago. And then left it for several years, and then have just come back to it quite recently with Kevin Kiley, who's a PhD student in UCD where I am, and also with my former PhD advisor, Adrian Otwell. And Jose has also been helping us with some of the things we've been doing more recently. So I'm going to talk about GreenFunctions and Hadamard expansions and how they relate to Riemann Tensor Canonicalization. I'll maybe just give people a little bit of an explanation of the first two parts here, the GreenFunctions and Hadamard expansions, and what I mean by them. So there are a few things that we need to set up before we start talking about GreenFunctions. So I'm going to define a few quantities and show how they generalize things that we're used to in most physics courses. So the first thing I'm going to introduce is this thing called the Sing world function. This is just a function which measures the distance between 2 points. So if you've got a point x and a point x primed up to a factor of a half, the world function sigma is the square of the distance between them. And in relativity, when we talk about distance between points, we need to define exactly how we measure that distance. And in the case of the world function, it's distance along the geodesic that connects the 2 points. If you take a derivative of this world function, well, it's a function of 2 points, of x and of x primed. So you can take a derivative with respect to x or with respect to x primed. What you get is a vector. So we usually denote the covariant derivative with a semicolon. Because we're going to encounter so many derivatives of sigma in these slides, we usually leave out the semicolon. And then anytime you see an index on a sigma, read that as covariant derivative of sigma. So that derivative is a vector, and it turns out that it is the vector which has length being the distance between x and x primed, and pointing oriented in direction from x primed to x. So I've denoted those vectors here by the blue arrows. This world function sigma satisfies a fairly simple equation that 2 times it is equal to the contraction of its derivative with itself. So sigma A is 2 sigma. And then so you can think of these as equations which also have initial conditions. And the initial conditions are that the distance between 2 points when you bring the points together is 0. And that the second derivative of the distance between the 2 points as you take the limit of the points going together is just what we mean by the metric. So that's the world function. It measures distance between points. Another thing we encounter in the calculations I'll talk about is something called the bivector of parallel transport. This takes a vector at point x, here's the vector TA, and it parallel transports it along the geodesic from x to x primed and allows you to define a vector at x primed just by contracting the first vector with this bivector of parallel transport, GA primed A. This bivector of parallel transport is defined through a transport equation. Its derivative, covariant derivative, projected along the direction along the geodesic is 0. In other words, it is parallel transported along the geodesic. Along with the initial conditions that when you bring the points together, this bivector of parallel transport is the metric. And then if you go back to the definition of what a geodesic is, that allows you to use the bivector of parallel transport to take a sigma vector at 1 point and up to a minus sign and transport it to a second point. Okay, so the last thing I want to introduce, the last fundamental biotensor is what's called the Van Vleck-Moret determinant. And this is a scalar which measures the focusing of neighboring geodesics. So if you have 2 points here, x and x primed, then the geodesics, two neighboring geodesics of x will either go parallel to each other, or they might converge, or they might diverge. And that's measured by this thing, sigma, which is the determinant of the matrix of second derivatives of sigma. And this Van Vleck determinant also satisfies a transport equation, which is that its derivative along the sigma direction, so the square root of it actually, this d prime just means take a covariant derivative and then project it along sigma, is equal to 1/4 4 minus the box of sigma times delta to the half. So you can think of this as an ordinary differential equation defining sigma along GD, defining the Van Dyck determinant along a GD-SIC. Okay, so why is all that stuff useful? What we're going to be doing is considering green functions, and we're going to be taking series approximations to green functions. These are going to be in curved spacetimes. We need to have a generalization of the idea of a Taylor series, which we encounter all over the place, to the context of curved spacetime and relativity. So in flat space, well, what's the distance between 2 points? It's just the magnitude squared of the vector, of the difference between the vector connecting the 2 points, x prime minus x. So, and the derivative of sigma is a vector, which is the vector going from 1 point to the x prime minus x. So with sigma here, we can generalize the idea of a Taylor series, which is if you have a function a of x and x primed, then you can expand that function in a Taylor series where you've got a set of coefficients here, these a's without any with indices on them, times delta x's, or in our case, sigma a's, sigma alphas. So this is the generalization of the idea of a multi-dimensional Taylor series to the case where you want things written in a covariant way in terms of covariant quantity sigma. We can use a shorthand that each of these terms in the series, these a contracted with sigmas, is just a sub k. And then you've got the standard rules for infinite series that, well, the one at the bottom is very standard. If you multiply two infinite sums, then you can write that as a sum of products with a binomial factor in it. You can also differentiate these a series along the sigma direction, and that just has the effect of multiplying the kth order term by k. Okay, so that's kind of the mathematical machinery we need. Now, just to introduce the idea of a Green's function, these are things we encounter in physics all the time. We deal a lot with wave equations. Here's the scalar wave equation. Box of some scalar field phi is equal to minus 4 pi rho, where rho is the source. One way we can solve this equation is by using the Green's function. So if we have a Green's function, a fundamental solution to the equation given by box of the Green function, which is a function of 2 points now, is equal to minus 4 pi times the Dirac delta of x and x primed. If you can solve this equation for g, then you can find any solution for the scalar wave equation with any source you want by convolving with g. So a given solution 5x is obtained by integrating g times the source over the full spacetime. That's in flat space. Well, this is a general statement. In flat space, green functions are easy to find. They basically just tell you how things propagate along null GD6 from one point to another, and null GD6 in flat space are straight lines. In curved spacetime, things are more complicated. Null GD6, or the light cone in curved spacetime, is complicated. For example, if you think about a Schwarzschild black hole, which would be kind of represented by the cylinder in the middle of this left diagram, then the light cone of some point here at the vertex in Schwarzschild spacetime has this very complicated self-intersecting kind of structure. So that's going to complicate the green function in one sense. And on the right is the Kerr case, which makes it even more complicated. You add a bit of rotation into the. So this is just to say that the green function in curved spacetime has quite a lot more structure to it, and it's more difficult to find than the flat space one. And that's largely, here's another plot of a similar thing. If you take a slice through one of those light cones and you plot the green function, you can see that it has support not just on the kind of the light cone, which is the null GD6, but also everywhere else in the spacetime. So that doesn't preclude us from being able to try to compute the green function. In fact, there's one very nice way to do it, which is that if the points x and x primed are close enough together, I won't define precisely what that means, but essentially if there's one GD6 connecting them, a unique GD6, then we can write it in this Hadamard form, where it's a combination of two pieces. There's this piece here, which the important bit you want to read out of here is that there's this delta of sigma. Sigma is 0 when the distance between 2 points is 0. In other words, when they're connected by a null GD6. So this delta function has non-zero support only on the light cone. So this represents propagation along null GD6 of the scalar field, for example. Now, because it's a curved spacetime, as things propagate along null GD6, if those GD6 are expanding or contracting, then you don't just get a 1 here like you would in flat space. So in flat space, we'd have delta to the half as 1, and you just have this delta, and you wouldn't have this second term at all. In curved spacetime, this delta to the half now captures the fact that as things propagate along GD6, it gets focused or defocused. Then the second part that's new in curved spacetime is this extra bit. This has a theta function, a step function, that has a minus sigma inside it. So it's only non-zero. The step function is only non-zero inside the past light cone. So the first bit's on the light cone and the second bit's inside the light cone. And again, there's another function here, I'm going to call it v, which is not yet determined. So we have this green function, this Hadamard form green function that seems nice, but we really just moved the problem onto figuring out how we're going to solve for delta to the half and v. Well, it turns out that there's a way you can do that using transport equations of the type we saw earlier on in the talk. So in fact, this v here, this term in front of the theta, you can write that formally as a series in sigma. So it's a sum of terms, VR times sigma to the power of r. So here the r here means raised to the power of rather than covariant derivative, just for clarity. So this is a power series in powers of sigma. The thing about that is you can write down equations for these VRs, which are transport equations. They're ordinary differential equations along GD6. So the first term is given by the derivative along the GD6 of V naught plus an extra term involving V naught plus a term involving the box of the Van Dyck determinant is equal to 0. This is an ordinary differential equation, a transport equation for V naught. And likewise, you can write down similar transport equations for all the other terms in this Hadamard series. And these Hadamard coefficients turn out to be the thing that we really want to compute to be able to get the green function curve spacetime. And they're also closely related to what are called DeWitt coefficients and heat kernel expansions. So the question is then, how do we actually solve these transport equations for the V naught and VRs? Well, there's an old-fashioned way, or a traditional method, which is basically you start from this equation for sigma, the defining equation for sigma, you differentiate it a load of times, and then take the limit as the points go together. And if you need to go up to a certain order, say order sigma to the power of s, then you need to take 2r plus 1 plus s derivatives of sigma. And that sounds fine, but you can see here a scan I took of my former PhD advisor's work when he was working on this before I started my PhD, doing it all by hand. And I don't expect you to be able to read that, but the point here is that these are very long, complicated calculations, very prone to error, very naturally applicable to computer algebra. So very, very, very rapidly becomes impractical to do these calculations by hand. And even using computer algebra, when I started working on this, I started using xAct to do this algorithm. And it sort of worked, but even then it was very inefficient. So the solution is that there's a better method. And that better method was published about just over 10 years ago now in this paper, where we wrote down a set of transport equations, and we were able to use that to directly solve for the V's rather than going through this kind of differentiating and taking limits approach. That paper came with a package called covariant series. It's a Mathematica package that computes these V's for you and gives them in terms of the Riemann tensor. In principle, that's great, but the problem is that the results you get are not necessarily in the simplest possible form. So this covariant series package will spit out an expression, but it's not simplified. More precisely, it's not in a canonical form. So not only is it not small and compact and easy to put into a paper, it's also very difficult to check if it agrees with someone else's calculation of the same thing. So this is where xAct came in for the second time in this project. We used it to take the expressions that were generated by this covariant series package and canonicalize them. Now, xAct on its own does very well with canonicalization, but it only knows about single-term identities of the Riemann tensor, effectively. So any symmetries of the Riemann tensor that involve more than, relating more than one term with another one, so 3 terms, for example, are not captured by the algorithms built into xAct. And unfortunately, the Riemann tensor actually has an additional symmetry, which is the Bianchi identity. And this is a term relating 3 Riemann tensors to each other. So on top of xAct, there is a package called invar, which is part of xAct, which basically, by essentially a brute force method, teaches xAct about the Bianchi identity. And it allows you to canonicalize things into the simplest possible form. So with that, I think I'll just switch over to Mathematica and actually give a demonstration of this covariant series package and how I use invar to simplify the results. First thing I'm going to do is load the covariant series package. I will then load invar, and I'm going to define this rule, which is to do with the potential and the wave equation. I'm not going to worry about that. If we now go down and ask this covariant series package to compute V naught, it will do it. It will spit it out in this specialized notation that we invented for this calculation. To make it more clear what this really means, we can convert it to what I call X-tensor format. So this covariant series package hooks into X-tensor in that it can generate X-tensor expressions directly. So if we take that thing and convert it to an X-tensor expression, we see that V0 is actually 1/2 the square of the mass plus or minus 1/12, essentially the Ricci scalar. And we can simplify that to change the Riemann tensor into a Ricci scalar. Okay, so that's V0. It looks like there's nothing wrong yet. What about when we go to higher orders? Well, V1 is a bit more complicated. The expression in terms of Riemann tensors also becomes more complicated. And now you're starting to hopefully see that this is not the sort of thing I would want to do by hand. Fortunately, 2 canonical is enough to sort out most of the simplification, but not completely. And we see that if we use Riemann simplify, which is the invar command that also uses the Bianchi identity, it reduces this fairly simple expression into something even simpler. So the first part is that simplifies it, but it also, if I wanted to compare this against some existing calculation, I could subtract the 2, and only if I had Riemann simplify available would I know for sure that they agree with each other or not. And just for demonstration, we can go to 1 order higher where things get a bit more complicated. Generating the X-tensor expression is quite painful. It doesn't even fit in the, we'll print it out by default. If we canonicalize it using 2 canonical, it at least gets it down to the point where it will print on my screen, but it's still not in the simplest possible form. There we go. So the canonicalized version is this, but we have not yet applied the Bianchi identity. We're now going to apply the Bianchi identity and using Riemann simplify, and we'll see that we get an even simpler expression, which is in what's guaranteed to be a minimal canonical form. So simplest, in some sense, the simplest possible form. Get rid of the messages. You can see that it is indeed a shorter expression than the one above. I'm just going to take out of the paper we published this table, which lists how far we went. So I've just shown you V0, V1, and V2, and the covariant series code just generates 2 terms, 10 terms, and 91 terms for those things. Once we canonicalize using Riemann simplify, we see we get down to 2, 4, and 15. So the V0, it doesn't make any difference. It makes a bit of difference for V1, and it's starting to make a very significant difference for V2. So remember, each of these terms is a polynomial in the Riemann tensor. If you go to V3, you discover there are 1,058 terms, but actually only 68 of them are unique or independent. We also went up to V4, so we generated 13,972 Riemann tensor terms, simplified them down to just 380. V5, we generated about 200,000 terms, and V6, we went up to about 3 million Riemann tensors. We weren't actually able to canonicalize them at the time, not because xAct couldn't do it, but because we didn't have enough RAM. This was 15 years ago. We should really revisit this calculation and fill in these 2 ones here. The table, the set on the right is where you canonicalize and you assume a vacuum spacetime where the Ricci tensor vanishes, so you get fewer terms again. And we were able to go a little bit higher order in that. But you can see that you're getting at least a factor of 100 improve simplification in the expressions. And we went up to V8 where there were 6 million Riemann tensor terms in the expression. I guess showing the power of really pushing xAct to the limits. I was a bit sneaky here because I only showed the green function for the scalar wave equation. So where you've got a scalar field. The universe isn't made out of just scalars. In GR, in electromagnetism, we're interested in vectors, and in GR, we're interested in tensors typically. So you can write down equivalent equations for vector fields and for tensor fields. Good news is that the same ideas work in this case, but the bad news is that we now have free indices to worry about. And the problem this brought up was that invar, as it currently stands, does not know how to canonicalize Riemann tensor expressions where there are free indices. You can only do things which are scalars. So this was a bottleneck back when we initially did this. Fortunately, implementing a new package, which is coming soon to xAct. We have a kind of an internal version working at the moment. We need to polish it up and then release it quite soon, called tinvar, and it's basically an extension of invar to also be able to canonicalize Riemann tensor expressions with free indices. So let me do a quick demonstration of tinvar just to show you that it works in the same kind of way. So I'm going to do some setup here, loading. The most important thing is we're loading this new package, tinvar. Kevin also implemented a version of the covariant series package, which works with the vector wave equation rather than the scalar wave equation. So I'm going to load that. And now let's go through the same thing we did in the scalar case, but now for the vector green function. So V naught now is something with two free indices. So how can you get that? Well, you can get either a Ricci tensor or a metric times a Ricci scalar. We can Riemann simplify that, and it doesn't change. So that one is doesn't really get much benefit. We could also, let me actually skip to the next one, V1, but we can see that this has now generated a expression involving Ricci tensor squared and Riemann tensor squared, and then we can simplify that, Riemann simplify that, so canonicalize, including Bianchi identity, and get that down to a expression which is shorter. Now, rather than going on to V2, what I'll actually do is compute this thing V01, which is another off-diagonal parts of the V's. So the V's are defined in the coincidence limit. These are the off-diagonal parts. You don't take coincidence limit. Here's one where, again, we have a expression involving the Ricci tensor and Riemann tensor with free indices. We'd like to simplify that. So Riemann simplify will do the job nicely, and we'll get it down to something simpler. It's not much of a gain here, but as has been the case throughout, it's when you start to go to higher orders that things become more painful, and the gain of using Riemann simplify, this simplifies down quite a lot once you use Riemann simplify. So let me just leave up some concluding slides to say that GreenFunctions are a great way of solving problems involving the wave equation. Geometric methods based on bitensors are a good way to compute GreenFunctions, and the applications of all this stuff is quite wide, from quantum field theory and curved spacetime to self-force models for binary black hole spirals.